Welcome to today's paper reading. Today's paper is titled MM-LLMs, Recent Advances in Multimodal Large Language Models. This paper, published on the AR14 preprint, presents a comprehensive survey on the recent advancements in multimodal large language models, MM-LLMs, by Duzhen Zhang and colleagues from Tencent AI Lab, Kyoto University, and Mohammed bin Zayed University of Artificial Intelligence. The abstract highlights the significant advancements in multimodal large language models, MM-LLMs, over the past year. These advancements have been achieved through cost-effective training strategies, enabling off-the-shelf LLMs to support multimodal inputs and outputs. The resulting models not only maintain the inherent reasoning and decision-making capabilities of LLMs, but also extend their utility to a wide range of multimodal tasks. This paper aims to provide a comprehensive survey to facilitate further research in this area. It begins by outlining general design formulations for model architecture and training pipelines. Additionally, it introduces a taxonomy of 126 MM-LLMs, each defined by its specific formulations. The survey also reviews the performance of selected MM-LLMs on mainstream benchmarks and summarizes key training recipes to enhance their effectiveness. Finally, the paper explores promising future directions for MM-LLMs and maintains a real-time tracking website for the latest developments in the field. The authors hope that this survey will contribute to the ongoing advancement of the MM-LLMs domain. The introduction of this paper highlights the significant advancements in multimodal MM pre-training research, which have consistently pushed the performance boundaries across various downstream tasks. However, as the scale of models and datasets continues to expand, traditional MM models incur substantial computational costs. Recognizing this, the paper introduces the concept of MM-LLMs, which capitalize on pre-trained unimodal foundation models, particularly large language models, LLMs, to mitigate these computational expenses. The core challenge in this field is effectively connecting LLMs with models and other modalities to enable collaborative inference. The paper also notes the predominant focus on refining alignment between modalities and aligning with human intent via MM pre-training, PT, plus MM instruction tuning, IT, pipeline. Figure 1 presents the timeline of multimodal large language models, MM-LLMs, from April 2022 to February 2024. It highlights key models such as Flamingo, Blip2, PaLM, and Visual ChatGPT. The timeline also marks the emergence of models capable of any-to-any modality conversion, indicating advancements towards artificial general intelligence. The model architecture of MM-LLMs consists of 5 key components: the modality encoder, input projector, LLM backbone, output projector, and modality generator. For training, the modality encoder, LLM backbone, and modality generator are typically kept frozen, with the primary focus on optimizing the input and output projectors. These projectors are lightweight, contributing to only about 2% of the total trainable parameters. The modality encoder handles various input modalities such as visual, audio, and 3D data, using specialized encoders like NFNet F6, VIT, and ClipVit for images, CFormer and Hubert for audio, and ULIP2 with PointBERT for 3D point clouds. Figure 2 illustrates the general model architecture of multimodal large language models, MM-LLMs, and the implementation choices for each component. The architecture is divided into 5 main components: modality encoder, ME, input projector, IP, LLM backbone, LLM, output projector, OP, and modality generator, MG. The modality encoder is responsible for encoding inputs from diverse modalities such as images, videos, audio, and 3D data to obtain corresponding features. The LLM backbone processes these representations, engaging in semantic understanding, reasoning, and decision-making regarding the inputs. This architecture allows MM-LLMs to efficiently train and empower various multimodal tasks. The training pipeline of MM-LLMs is divided into 2 main stages: MM pre-training, MMPT, and MM instruction tuning, MMIT. During the MMPT stage, the X-text datasets, which include image text, video text, and audio text pairs, are used to train input and output projectors. The optimization focuses on aligning various modalities using predefined objectives, specifically equations 2, 4, and 5 for generation models. The MMIT stage involves fine-tuning pre-trained MM-LLMs using instruction-formatted datasets, which enhances their ability to generalize to unseen tasks. This stage includes supervised fine-tuning, SFT, and reinforcement learning from human feedback, RLHF. SFT converts part of the PT stage data into an instruction-aware format, while RLHF further fine-tunes the model using feedback. The datasets used in both stages are subsets of the comprehensive datasets listed in Tables 3 and 4. The authors classify 126 state-of-the-art multimodal large language models, MLLMs, from both functional and design perspectives. In the design division, tool using denotes treating the LLM as a black box and providing access to certain multimodal expert systems to perform specific tasks via reasoning, while end-to-end signifies that the entire model is trained jointly in an end-to-end manner. Based on these design formulations, the authors conduct a comprehensive comparison of the architectures and training dataset scales for 43 of these SOTA MLLMs. The developmental trends in existing MLLMs show progression from multimodal understanding to the generation of specific modalities and further evolving into any-to-any modality conversion. The training pipeline advances from multimodal pre-training, MMPT, to supervised fine-tuning, SFT, and then to reinforcement learning from human feedback, RLHF, striving to better align with human intent and enhance conversational interaction capabilities. Additionally, there is a trend towards embracing diversified modal extensions, incorporating higher quality training datasets, and adopting more efficient model architectures. Table 1 provides a comprehensive summary of 43 mainstream multimodal large language models, MLLMs. The table details the input-to-output modalities, I/O, where I stands for image, V for video, A for audio, 3D for point cloud, and T for text. It also includes specifics about the modality encoder, such as the size and resolution of the models, and the scale of datasets used during multimodal pre-training, MMPT, and instruction tuning, MMIT. This table is crucial for understanding the current state of the art in MLLMs and their technical specifications. In this section, we present a comprehensive performance comparison of major multimodal large language models, MLLMs, across 18 vision language, VL, benchmarks. This information is summarized in Table 2 and detailed descriptions of these benchmarks are available in Appendix F. We focus on evaluating and comparing different MLLMs based on key benchmarks such as OKVQA, IconVQA, and VQA-V2. OKVQA requires reasoning with various knowledge types, where MiniGPT-V2 and MiniGPT-V2 chat perform best. IconVQA emphasizes abstract diagram comprehension, again where MiniGPT-V2 and MiniGPT-V2 chat excel. VQA-V2, a balanced VQA dataset, is best performed by VILA 13b. Additionally, we discuss training recipes that enhance the effectiveness of MLLMs, such as using higher image resolutions and incorporating high-quality SFT data. For instance, LLVA 1.5 and VILA employ higher resolutions, and the addition of ShareGPT-4v data significantly improves performance. PFD on the LLM backbone is also crucial for in-context learning, ICL. Table 2 presents a comprehensive comparison of mainstream multimodal large language models, MLLMs, across 18 vision language, VL, benchmarks. The benchmarks include OKVQA, IconVQA, VQA-V2, GQA, VisWiz, SQAI, VQAT, POPE, MEP, MEC, MMB, MMBCN, CD, LLVAW, MMVET, QBench, HM, and VSR. The table highlights the highest and second highest results in red and blue, respectively. Notable performances include MiniGPT-V2 and MiniGPT-V2 chat excelling in OKVQA and IconVQA, showcasing their outstanding reasoning and cognitive reasoning abilities. VILA 13b demonstrates superior ability to comprehend multimodal information and resist language biases in the knowledge it acquires, performing best in VQA-V2. LLVA 1.5 and VILA 7b illustrate their excellent reasoning abilities in the domain of GQA. The future of MM-LLMs involves several key directions. Firstly, enhancing MM-LLMs can be achieved by expanding the range of supported modalities, diversifying the types and sizes of LLMs, and improving the quality of MMIT datasets. Secondly, to truly challenge the capabilities of MM-LLMs, it is crucial to construct larger-scale benchmarks that include additional modalities and employ a unified evaluation standard. Lastly, for deployment on resource-constrained platforms, such as mobile and IoT devices, lightweight implementations are essential. This includes strategic downscaling of models and the use of lightweight downsample projectors to improve computational speed and efficiency. In this paper, the authors have provided a comprehensive survey of multimodal large language models, MM-LLMs, focusing on recent advancements. They categorized the model architecture into 5 key components, offering a detailed overview of general design formulations and training pipelines. The survey also introduced various state-of-the-art MM-LLMs, each distinguished by its specific formulations, and discussed their capabilities across diverse multimodal benchmarks. The authors highlighted the potential social impact of MM-LLMs, including enhanced accessibility for individuals with disabilities and the revolutionization of education and media. However, they also noted the risks associated with privacy concerns and biases in AI algorithms. Despite the comprehensive exploration, the authors acknowledged the dynamic nature of the field and the potential for omissions. To address this, they established a dedicated website for real-time tracking of advancements, aiming to evolve it into a continuous source of contributions. The authors are committed to vigilant monitoring and continual enhancement of relevant details on their website. Thank you for watching.